Good. Good. Okay, today we are glad to have Dr. Ashok Gopalakrishnan from Siemens. He has over 24 years of experience in power system analysis with focus on protection and control consulting services. He is currently the head of the integration and services for grid resilience products at Siemens, including PSSE-K. Prior to transitioning to this role, he was the director of PSSE-K software product group for 3 years. And before that, he was at Siemens PTI and Quanta Technology. He was involved in protection and control consulting services, including regulatory compliance, protection process, automation, and protection security assessment through software solutions. Since from 1999 to 2014, he was with the Electrocon International, which right now is part of Siemens. Basically, that CAPE software is coming from that group, Electrocon International, and was a key member of the PSS CAPE engineering team. So Ashok has contributed a lot to this software. So I'm sure today we learn a lot from him. And Ashok was from the same group that I got my PhD from, so from Texas A&M. So, but he's of course much more senior to me. So today we are here to learn a lot from Ashok. So Ashok, get back to you. Yeah, floor is yours.
Okay, perfect. Thanks, Saeed, and really appreciate the opportunity to talk to this seminar class at WSU. My talk will focus on some methods to analyze and visualize the performance of the protection system. I have a few slides, but I would like to keep the focus more on the practical aspect of things and the software itself. So I hope that makes it more interesting for the students. So the outline, I'll talk very briefly about what Siemens Grid software is and the role of myself and my team in it, and then get into a few protection concepts like protection sensitivity and selectivity. And then once we get over those concepts, I'll talk a little bit about how we perform coordination protection evaluations in transmission and distribution systems. Again, I won't have time to go into the distribution side, but definitely a little bit we'll spend on the transmission systems, and the concepts can be extended, of course. And then I'll like to do a demonstration, show you practically how a utility may perform such studies. And then towards the end, I'll get into how we can combine the dynamic behavior of the power system and how that impacts protection, especially when you consider that we have a high penetration of inverter-based resources, not only in the distribution system, but also at the utility grade, transmission level. There's a lot of penetration, and that has an impact on both protection behavior and power system dynamics. So I'll spend a little bit of time there as well. And then definitely leave some time for Q&A. You're recording the presentation, that's great. And then if there's interest, I can also share my slides with the group once our meeting is over. So what is Siemens Grid software? Well, before we get to that, here's a little bit about me. I know Saeed gave a good introduction, so you can read all about it here. But I did spend quite a bit of time at Texas A&M with Mladen Kazunovich's group, and a couple of the members in the CAPE team received their PhDs from there, and as did Saeed, as you know. So we have good connections, and Mladen does a good job of keeping us all together. We'll get periodic emails, and we participate in some occasionally in meetings and stuff. So anyway, that's a bit about me. I actually live in the Boston, Cambridge area in Massachusetts, whereas the CAPE team is based in Michigan. And as you know, these days, having people spread out and working remotely and interacting in person as needed is very common, and it's worked out well for us so far. Now, when we get into the Siemens portfolio or Siemens grid software, as we call it, right, SIGSW, there are many software tools that are available in our portfolio. And you may be familiar with some of them, at least PSSE, probably a lot of you know. It's our industry standard software for transmission planning and operations studies. You can perform load flow or transient stability types of calculations with it, and more recently, harmonic studies, power quality studies as well. SynCal is more suited for distribution systems. You can perform IBR penetration studies with it, and then where you can actually cite inverter-based resources for optimum use. Many different distribution types of planning and studies can be done with SynCal. Then I'll come to PSS Cape and Seaguard in a second. And then we also have PSS Mod for managing and exchanging data, network data in PSSE format. And then PSS ODMS is a more standards-based modeling software for primary network systems. So the SIM is what is known as the Common Information Model. It's an IEC standard. And it has there's a standard way of representing transmission lines, transformers, etc. So it makes it easier for exchanging data with different software vendors. Now coming to PSS Cape, it was a recent acquisition by Siemens. Recent meaning 2018, so more than 5 years ago, Siemens acquired Cape from the company Electrocon. And it stands for Computer-Aided Protection Engineering Software. You can perform detailed protection studies, short circuit calculations, etc. with it. And that's where my focus is on. I was part of the engineering team for many years and was leading the team as well for some time, and still of course work with Cape. And recently also started looking at this product called Seaguard, which is just Siemens Guard. It's a grid dynamic security assessment tool that looks, tries to grab phasor data and marries that information with dynamic studies and that performs dynamic security assessments. So while I'm most familiar with Cape, our team is slowly starting to pick up Seaguard as well, and we'll be in the future, delivering projects using this tool as well. So Cape and Seaguard are part of the grid resilience, and going back this slide, I'm the head of integration and services for grid resilience products within the Siemens Grid Software Group, and that includes Cape and Seaguard, right? So those are the items in my portfolio. Okay, we also perform consulting services. For various clients, we develop and validate their primary network models. And as you know, primary network models include the representation of the electrical system, right? Transmission lines, generation, transformers, inverter-based resources, loads, series capacitor banks or shunt reactors, shunt capacitor banks, and so on. So all that comprises the primary network model. So we do consulting services for building and validating such models for various customers. And then we also perform activities where we add the protection data on top of the primary model so that we can utilize Cape to perform various kinds of protection studies. So we offer consultancy services for building and validating protection models as well. We do a lot of work on interfaces to other programs and systems. For example, one of the projects we're working on right now is to combine CAPE with the geographical information system, GIS as you would call it, right? So so that we can lay out the diagram, the one-line diagram in CAPE in a geographic manner. So that's one of the interfaces we're working on, and we do, we are developing connections to SCADA systems or other systems that utilities have for operating their network. Then we do consulting services for relay settings calculations, and we actually also perform protection coordination studies that evaluate the behavior of the protection system, and then you have to adjust the settings for those relays to so that they behave in an optimal and reliable manner, right? So we offer these kinds of consulting services as well. Now let's jump a little bit into protection sensitivity and selectivity and talk about that. So I'm sure in your graduate coursework you'll have classes on protection. What are the principles of protection? How do you protect a system? Why it's needed? And so, as you probably already know, a protection system cannot prevent abnormal conditions occurring in your network, right? You have overloads, you have short circuit faults, dynamic events. Those things happen. They're natural phenomena. But what they can do is they can limit the damage that such abnormal conditions can cause if left to stay on your network without any mitigating action, right? So the protection system plays a very, very important role in the reliable operation of the power system. When there is a need for your system to be protected, you must have something there that does it. And that's where often when you do analysis, you may do load flow stability studies or reliability studies. Often the protection behavior may be ignored or not considered fully, and you could run into issues later. So the behavior of the protection system, how it works, does it do its job? Those are all important things for the engineer to study. And hopefully, some of you, when you graduate, will be working in a utility or with consultants, and you'll deal with such situations on a day-to-day basis. And with the increased protection of renewables and inverter-based resources in the system, the reliable operation of the protection becomes more and more critical in maintaining the reliability of the grid. I think a couple of seminars ago, Abu Talib from EPRI would have talked to you in detail about, as you lose system inertia, right, or as you see reduced levels of fault current, your conventional protection systems may not work reliably, and then you need to look at new ways to protect the system, and then that behavior becomes critical. And then lastly, what is the main goal of protection? Well, I always look at safety of human beings, right? You want to be sure that nothing happens in the system that can cause injury or fatalities for human beings. So safety is paramount, and that's where protection comes in. And of course, you also want to prevent or limit damage to equipment because it's expensive to replace, of course. And then you want to limit service disruptions, right? You don't want power to be lost. You want industries to be served, people to have power all the time. So one of the goals of protection is also to limit service disruptions when they do occur. And you want to limit them from both the duration perspective, how long is the power out, right? You want to limit that. And you also want to limit from a geographic perspective. You don't want that disturbance or the outage to spread on account of improper behavior of protection. And geographic perspective, you immediately think of blackouts or the grid shut down because your protection did not behave correctly. And so there are some common terms associated with protective relaying. You have reliability of the protection system, where you want it to operate for abnormal conditions within the area it's supposed to protect, also known as the protection zone, and you want it not to operate when the abnormal condition is outside of its area of purview, right? Whatever it's responsible for protecting. Or if there is no abnormal condition, again, your system should just be there ready to go, but it shouldn't operate when it's not needed. You will hear the term selectivity, meaning isolate only the problem area, leaving the rest of the system intact. You'll hear this term speed or sensitivity, isolate the problem area as quickly as possible to minimize the amount of time that abnormal condition stays on the system. Then your system should be simple, right? You want to use the most straightforward design for the application. You don't want to overcomplicate things by adding more and more functions when it's not needed, right? More components, more the chance of failure. So you have to strike a balance. And then economics is always an important part. You can add hardware, communications, fiber optics, all kinds of things, but you're making the system more expensive. And like it or not, engineering always involves that cost aspect that we have to consider. So the point I'm trying to make here is that, yes, there is definitely a science and there is mathematics, there's methodologies there, but at the same time, there's also some art where you have to compare, compare and contrast. If I spend this much money, am I getting equivalent benefit, or am I throwing money away? And those are the things that protection engineers deal with when they, set up their protection schemes, decide how to build the scheme, what equipment to use, and so on. Okay, so and then as I said, often you'll see, selectivity and sensitivity are at odds with each other. If you make your system super high speed and by increasing its sensitivity, then you are probably compromising on selectivity, meaning you want to restrict how far it operates. And there are ways to balance, and it's often you have to get the science down, of course, but you also have an art component to it when you work on designing these protection systems. Okay, so now we get into protection coordination studies and how we use, why do we need to do it, and how can we do it? Right, so the goal of performing these studies is to uncover and remove, mitigate hidden issues in selectivity or coordination or sensitivity before they actually occur in the system as a real relay misoperation, right? You want to, in a safe environment, which is essentially your computer, you want to run these studies and find them out and mitigate them before they actually occur as relay misoperations. And that's the overall goal. And protection engineers have been doing this for years, right? They've been doing this for many years, either manually or in automated ways. But now, past 3 to 3 years now, we actually have NERC standards. NERC is North American Electric Reliability Corporation, and they have many different legally enforceable with monetary penalties. They have standards that utilities must comply with. And this, demonstrating that your system is selective, it's coordinated, is now required by law, I guess, since NERC has the support of FERC, which is our federal government body that enforces these standards. So utility engineers have to perform these studies to comply with standards. And not only that, they want to run a good system, so they need to perform these studies. So what the study does is it evaluates the behavior of protective relays working together as a system, rather than as just simple pairs. Often you may evaluate a primary protective relay with a backup relay and say, okay, they're coordinated, we're done. But there's more to it than that. You have to evaluate the protection as a system and see if there are any holes in your protection philosophy that you need to mitigate. And this is done by challenging the system with a large number of faults, meaning short circuit conditions. You're used to seeing single phase to ground, three phase, or double phase to ground faults. So you apply these faults at many different fault locations under many different system contingencies to try and uncover issues that exist in your protection system. Okay. And we use a technique, and Kate uses this, and I'm sure other tools do too. We use a quasi time domain simulation that starts from fault inception until fault clearing. So I didn't mention this before, but typically short circuit programs like CAPE and other tools that you have, they use a single frequency phasor-based calculation. So you basically have a 60 hertz or a 50 hertz system, and then the way you calculate faults is you have your Thevenin pre-fault voltage at wherever the fault is applied, and then you have the Thevenin impedance that's determined from how what kind of fault it is and which are the sequence circuits, positive, negative, or zero, that are involved, and then you calculate the fault current. So it's a single frequency phasor-based calculation, or you could even think of it as a steady state calculation. So it's not a true time domain simulation, and that's why we call it a quasi time domain simulation. We study the protection system responses with a series of steady state conditions. So the way we do it is we apply a fault, then we calculate the relay behavior and open whichever circuit breakers need to open, right? And when you open the circuit breaker, the system topology changes. You now have a redistribution of the fault currents. And now new relays may operate. Relays that were predicted to operate before may drop out and stop operating, and other breakers will now open. So you basically do this go from one circuit breaker operation to the next until the fault is completely removed from the system, or no more circuit breakers or relays can operate. So it's a quasi time domain, and it goes from one breaker operation to another. And we do have a demonstration, so you'll be able to see how this whole technique works. So we are able to simulate what we call sequential fault clearing, going from one breaker operation to the next. And we try to find out what the problems are. And we look for basically three kinds of problems. Right? We look for situations where the coordination time interval is violated. And when we say the coordination time interval, what it means is that you have a relay that has got primary responsibility for clearing the fault, and you have another relay that does not have primary responsibility. It's located elsewhere, and it needs to be there in case the primary doesn't operate, but it needs to be far enough away usually in terms of time compared to the primary relay. So if you have that kind of margin, then you know that, yes, if my primary relay operates, my backup sitting somewhere else can see that fault, is sensitive to it, but it is slower, so that if needed, it can operate, but it will not operate as in the first resort. But utilities will typically use a margin of 250 to 300 milliseconds, or 0.25 to 0.3 seconds as the margin. So that's one kind of problem we want to find, and then we also want to find another problem called a miscoordination, where you now have a relay that operating elsewhere in the system when it should not operate at all. Right? It operates and opens its breaker, And we don't want that to happen. That goes to the selectivity of the system, right? You want the relay to operate only if it is responsible for the abnormal fault condition. And there can be a third situation where your relays don't have enough sensitivity to detect the fault condition. That can happen as well. And that is a problem too, right? You want to know if there is a situation where there are no protective relays available to clear the fault. So you want to know about that as well. So how do you do this, right? You have to subject the system to many fault cases. You can vary the generation level. You can perform system contingencies. You can vary the fault location, as you can see along the line. You can vary the fault type. You can vary the fault resistance, and you can even perform protection contingencies. What if a CT or a current transformer or a voltage transformer fails? How does that impact protection behavior? So you end up with these, even for one single transmission line, you end up with thousands of combinations of studies that you need to perform to make sure that your protection system behaves properly. And that's where automation comes into play. Here's another pictorial view of this thing. You build a scenario. What do you want to study? And then you impose that scenario on your system, and it performs all your protection simulations, evaluates the fault clearing sequence, and then you look at the results, right? And you'll see in the demonstration we use a kind of a traffic light approach where red indicates there's a problem, and then there are different colors for different types of problems found. So this is the visualization of the result and the identification of the vulnerabilities. And then there is another step, which is, okay, analyze the impact of the vulnerabilities found, and then the mitigation action, which is a separate activity. Right, so with that, I'll come back to the presentation, but let me switch over to the software itself, and you can see how it works. I thought I had started it, but no worries, I'll restart. So I'm starting the CAPE program. I won't obviously be able to go through all the features of it. So I'm going to jump right into the portion where we can actually run the analysis and look at the results. So what I've done is I've attached or connected to my electrical system representation. This is just a one-line representation of it. And I switch to another module or portion of CAPE. And here we can perform our protection coordination studies. So first thing I'm going to do is set up the scenario that I want to run. I'll take you through some basics. I hope you can see this clearly. So you remember how we want to consider different fault types and fault locations and so on, right? So here I'm looking at a single phase to ground and a three-phase to ground fault. Those are commonly studied by protection engineers. You can add other fault types as well. And you can add faults with resistance or arc resistance, which are often evaluated by engineers. Right, so those are the fault types. Then I have my fault locations here. I picked 3 of them, as you can see. There is a local close-in and a remote close-in, and I can go up to 5 different midline locations. But I chose 3 for this demonstration. And just to line it up with our slide deck, right? If I go back here, it's these locations where the fault is going to be applied, right? That's what I'm specifying in here. I'm specifying where I want these faults to be applied. these could be at 10, 20, 50, 80, 90%, and so on. So in this case, for any one single line, I've got 2 faults and 3 fault locations, right? So that gives me already 6 different fault cases to study. And for each case, I want to evaluate whether my protection behaves correctly. There are some other options here, probably not relevant now, but important in some cases. And then we also have to look at contingencies, right? What are the contingencies we want to study? And there are what we call the application-defined contingencies, which will allow you to outage automatically. You can outage lines that are connected on the study line. These are, how should I say, sources that are contributions to the fault current. And here, these are the primary system contingencies, right? You can outage a source that's connected here. If you have a parallel line, you can remove that line from service, or you remove a source at the other end. Or if you have generation in the middle, you can remove that. Now, why do we do these contingency studies? It's because that your system, you have a system normal condition, right, where the system normally operates, but there'll always be situations where some line is out of service for maintenance, or some generation or transformer is out of service for maintenance. And with those outage contingencies in place, you want to be sure that the protection system still operates properly and still is able to clear the fault. So in this scenario, in this contingency tab, I'm applying the contingency that will remove the lines that are connected to the transmission line under study, and it'll automatically do that. And then there are lots of other contingencies like outaging transformers, outaging generators, and removing mutually coupled lines, all kinds of things we can do. And the goal is, you're subjecting the system, the protection system and exposing it to different kinds of scenarios. And you want to make sure that the system is still able to clear faults with proper sensitivity and with proper selectivity. So these are what we call application-defined contingencies, meaning the program will determine by itself automatically what are the outages it needs to apply. And then there's also an option to perform user-defined, and these may be, in addition to the contingencies that the system determines by itself, you have the ability to add on more things that you want to simulate. Right, and some of our utility customers, they'll perform these studies periodically, every 3 months or 6 months, they'll run these studies on their entire transmission system. So you can, and we'll see, in this, let me run this example and we'll talk a little bit more. So now what I'm going to do, right, I've set up my scenario, and now I'm going to just pick this red colored 230 kV line from the center substation to the winder substation. And then I'm going to say, okay, right click the line and then say, just begin the study. And just do the study for this line, evaluate the protection, and also subject it to the various fault types and the contingencies. So you can see in the pop-up on the left, it says 42 different conditions will be simulated. But we had what, 2 fault types and 3 different fault locations, right? And then we added on the contingencies to it. So you basically have 6 different scenarios multiplied by the number of contingencies to be studied, and that gives you the 42 faults to be done. And it'll vary, sometimes on a line you may have more than multiple sources that need to be outaged, and each one Each line is different. Each transmission line is different. And this is what it's doing. It's going through all these 42 different faults, and it's finished. Now in here, this is our main result table. So we studied basically one 230 kV transmission line, right? And we applied two kinds of faults. We applied the single phase to ground, and we applied the 3-phase faults. And then we also said remove transmission lines that are connected to the terminals of our study line one at a time. So the program will perform the system normal calculation, right? That's this, and it will also remove connected sources at each terminal one at a time. So it removes the center to Gainesville line, then it removes the center to Bio, then it removes the winder to Lawrenceville, and so on, right? It keeps removing these sources or connections one at a time, and it studies the same fault conditions, same fault type and same fault locations, one after the other. And if you remember, we did 3 kinds of faults. We did the local close-in, and then we did a fault at 50% of the line, and then we did a fault at the remote close-in. So what you see here, right? Anywhere you see a green, it means everything is fine. Your fault was cleared in a specified amount of time, and you did not have any selectivity problems, meaning whatever was supposed to remove the abnormal condition did. And whatever that was not supposed to remove the or operate, it did not, right? So you have a lot of cases where the protection system behaved correctly, but you also have many cases, wherever you see these reds, right, where it says miscoordination, that is a problem because some other relay operated and removed some piece of equipment from service that it should not have. And you also had some CTI violations where a backup protection device was too close in time to your primary protection device. And that is something we want to avoid as well. So again, this is traditional, how should I say, traditional power systems analysis. It's what protection engineers in a utility will do every day almost. That's their job, to make sure that protection system behaves correctly. So it's traditional in that sense that people have been doing it for a long time, but it's also very important that they do this at regular intervals to make sure that their system still behaves reliably. And this is a tool that can help with that. So we can then go and see. If I want to get more details about that particular miscoordination, meaning what happened, why was there a protection system problem? So what I'm doing now is just right-clicking that particular cell, and then I'm going to ask it to run a more detailed study for that case, right? It's simulate in a certain module in CAPE. So when I do that, here is what happens, right? If you remember, I said we are running a quasi time domain study, right? We're starting with the initial fault, and then we're stepping through breaker operations. So what's happened here is that my first circuit breaker for this fault, right? This is the fault symbol. The circuit breaker opened at 3.5 cycles. And the system, the program has stopped right now. And then you see some timing at other locations, right? So those are the predicted operating times, meaning if I go from this point on to the next step, I'm going to see, hopefully, these devices operate. But what I'm also seeing is, my fault is on this transmission line. So I would hope that it's this protection over here and the protection at the opposite terminal, right? They are the ones we want to operate and clear the fault. But that's not the case. If I continue this one step further, and you see the background change color to a pink or something, and now I can see at this other terminal, at the 115 kV terminal, I'm seeing a breaker open, right? And that's exactly the kind of thing I want to avoid, because my fault is on the 230 kV line. So I shouldn't be seeing any operation like this from anywhere else in the system, but I am. In this case, I'm seeing some operation from this 115 kV side, which is not supposed to happen. And that's an example of a protection misbehavior that we want to avoid if we hope to keep our system running reliably, right? So in my main results, I saw there was a miscoordination, and when I dug deeper, I was able to say, okay, I have some operation from here that I should not have seen, and that's what the system caught. And you can then go one step further and try to find out what is the element that caused the misoperation, and then try to resolve, what was its setting? Is it, was it set too sensitively, or do I have to make some adjustments to it? That's the kind of further investigation that the engineer must do. So you and the hope is, once you have done the investigation and taken the mitigating action, all these reds will be changed to greens when you repeat the study with the mitigating action in place, right? So that's I think we should, at least for the transmission system, we probably should stop here, but you can extend this to multiple different lines. You don't have to stop at this one single line that I studied. You can automate this whole process so that it goes through your entire system and runs these studies and captures all the protection problems. To visualize this better, we have some tools to export the results to a spreadsheet, or you can save them, and you can the system actually accumulates this information historically, where you have over time, you can see how the protection coordination was affected, and you can retrieve previous results and see some statistical information and so on, right? So that's possible as well. And utilities will use this a lot to create documentation for proving to NERC that, yeah, they did the studies, this is what they found, and these are the mitigating actions they took, right? They can show all that. Okay, I know we've got only about 15 minutes, and so what I'll do is go to the next topic, which is the how do we include protect the system dynamics, right? The transient dynamic behavior of the system, power system, in protection studies. Right, so the example I showed you before was all running and using a single phasor-based calculation, right? At 60 hertz, there are no dynamics. We typically run with the subtransient impedance of machines to produce the fault current, and we don't account for any dynamic behavior of the protection of the power system. Loads have dynamic behaviors, machines have dynamic behaviors. We don't consider any of that. So what we do is, we have a way in which we combine the protection side of CAPE with the planning simulations that we can perform in PSSE, right? This combines the transient stability studies in PSSE with the protection simulations in CAPE, and does a co-simulation, meaning at every time step, we we interact, or let CAPE and PSSE interact at each time step, exchange information, and so that way we allow the transient behavior of the system impact the protection behavior, and vice versa. As relays operate and change the network topology, we pass that information back to PSSE, and so that the dynamics are again affected by the protection behavior. And we found this kind of simulation to be very, very useful, especially with increased IBR penetration, right? And one of the studies we did looked. This is a sample system, but you can extrapolate it and take it to larger systems as well. So this is a sample system that's actually being used by the IEEE PSRC working group D29. And in this system, there is a total load of about 2,100 megawatts. And there are a couple of conventional synchronous generation, right? This red box on this side and the red box over here. These are conventional synchronous generators. And what we did was converted them in stages from synchronous machines to inverter-based resources, right? And as you do that, you end up reducing the system inertia, right? The machines or the synchronous machines provide damping. They provide system inertia that helps keep the system stable. But as you convert, more and more of the synchronous machines to inverter-based resources, it reduces system inertia, and that has an impact on the critical clearing time, right? So the critical clearing time is when after a fault occurs, you have to clear that fault within a certain time. Otherwise, the system will go unstable, or you lose synchronism, and you'll have pole slips and all those other highly undesirable effects that occur in our power system. So with zero penetration of renewables, we saw a critical clearing time of 300 milliseconds. And as you increase the renewable generation level, we see that the critical clearing time keeps reducing, meaning your protection has to operate faster and faster as you introduce more renewable penetration into the system. So that's an interesting finding, and we now have to think of ways to new ways to protect, right? We can't use maybe distance protection anymore, or you may have to switch over to line differential protection all the time so that you have fast clearing. So there are some interesting challenges there that need to be explored, and the ability to combine the simulation, transient simulation, and PSSE with CAPE is very important. And we're also looking at the fact that the inverters have controls, right? Those controls behave not in the transient stability domain, they behave in the electromagnetic domain, which has an even faster response times. So it'll soon become not just CAPE and PSSE, but you may have to look at things like PSCAD or EMTP to be able to simulate such effects. So this whole simulation field is becoming more and more interesting and challenging to accommodate what's happening in the system. So we're about 4 minutes away. I'd like to reserve maybe 5 minutes for questions. So let me start a short movie on this CAPE transient stability simulation and how we can perform this co-simulation. So you can see a couple of examples. It's about
introducing the PSS CAPE TS-Link module, a tool that helps you perform transient stability simulations from PSSE using highly detailed relay models from PSS CAPE. Today, planning and protection departments typically operate in silos using unmatched and unsynchronized network data. Traditionally, the protection system is modeled in PSS CAPE using thousands of relays actively maintained by protection engineers, while the planning engineers use the detailed transient stability model in PSSE to study system dynamics and stability. The issue with this traditional way of work is that PSSE uses simplistic protection settings, which may lead to inaccurate conclusions in stability studies. And PSS CAPE does not take system dynamics into account. This may result in incorrect protection coordination conclusions, since the effective protection action over system stability is not included. With the PSS CAPE TS-Link module, you can break down these barriers and improve grid reliability. It provides a closed-loop simulation tool to evaluate system stability and protection settings together. This allows both planning and protection engineers to study the interdependence between system dynamics and relay actions. bringing together the best of both worlds. Here's how the PSS CAPE TS link works. After the simulation starts, at each time step, PSSE solves the current network operating condition with its transient stability calculation engine. Then the positive sequence solution is transferred to PSS CAPE. PSS CAPE interprets the PSSE solution and feeds it into the highly detailed relay models. The protective relays and the remedial action schemes are evaluated. If there is any protection operation causing breakers to open or close, the corresponding topology changes are transferred to PSSE. PSSE makes the same network changes to ensure the two programs are working on the same system operating condition. Then the simulation will advance by one time step, and the same closed-loop calculations will be performed. Here's a look at the PSS CAPE TS link in action. We'll simulate a real system separation event in a large utility. The three-phase fault caused by a lightning strike is applied 1 second after the simulation starts. 2 generator units have been outaged due to the fault. We see both the frequency and voltage at substation frost start dropping after the disturbance. The system's apparent impedance starts traveling towards the relay characteristics. The impedance is traveling slowly enough that a power swing blocking signal has been initiated. The Zone 2 and Zone 3 distance relays do not operate even after the apparent impedance entered their protection characteristics. About 2.2 seconds after the disturbance, the apparent impedance has exited the relay characteristics, which matches the timeline of the actual event. Several under-frequency relays start operating to shed load following the reduction in generation. This is part of the remedial action scheme, which automatically takes corrective actions to try to recover the network. In the second slip cycle, the apparent impedance is traveling faster than the first slip cycle, as the impedance travels a longer distance between 2 consecutive time steps. The out-of-step relay determines this is an unstable power swing, and an out-of-step tripping signal is initiated. The out-of-step relay will operate when the impedance exits the inner polygon characteristic, called trip on the way out. PSS CAPE strictly follows the manufacturer's relay operation logic and uses actual relay settings. Realistic protection operations are therefore assured. The last remaining 345 kilovolt tie line at substation frost is tripped on out of step. The utility network is now separated from the regional interconnect. This PSS CAPE TS link simulation successfully reproduced a very interesting event. This protection misoperation was only part of a cascade of misoperations that led to the entire network being islanded. Power system operators are particularly concerned about these types of events, and PSS CAPE TS link provides the details necessary to mitigate these misoperations. With this module, you can break down the barriers between transmission planning and protection tools to improve your grid reliability.
Siemens.
Okay, so again, that was a quick capture of an event we studied a few years ago. And that module, combining the stability and the protection behavior is very useful if you have to evaluate, out-of-step relaying, the loss of field functionality, different protection functions that you normally would not evaluate under just a steady state condition, right? What the traditional analysis that protection engineers do. And with the renewable penetration and less inertia in the system, it just becomes more critical to be able to do these kinds of studies. Okay, I think we have about 4 minutes, so I hope it was useful, and I'm happy to entertain any questions you have. I couldn't. Yes, sir.
This is Anil Jampala in online meeting with you. Thank you for organizing this event. You took me back 40 years to the early days of computer-aided protection. And you've done a very fantastic job of explaining all the nuances, challenges in this kind of tools. Thank you very much.
Thank you for that. Appreciate those words.
Yeah, okay. Thank you, Ashik. That was very informative, and always that's nice to see what's going on in practice in industry. So with that, let's go first to the people online. So is there any questions, people online? If you have questions, please unmute yourself and ask your question. If not, let's go people in the room. So anybody has questions? Sure.
So regarding the CTI coordination problem, I've also seen situations where like a protection panel has the primary side and the secondary side, where the primary side has all the line protection relay, traveling wave relay, the bus protection relay, and the secondary side has exactly the same thing. So the primary side is doing the same job the secondary side is supposed to do, and they are in the same location in the same panel. So I'm trying to relate this to what you said about CTI, where there might be some kind of miscoordination if the two relays are in the same location doing the same job.
Right. So the CTI that I talked about here was the CTI between your local relaying and anything that's a remote backup, right? So at a particular, on a transmission line, you have line protection, and if you have a line fault, that line protection is primary. Then in that case, your the local bus bar protection is a local backup. Whereas another relay at another substation becomes a remote backup. So we're traditionally in this kind of analysis, we're measuring the interval between your local backup and your local relay and your remote backup relay, and that's what we're measuring. We can tailor these studies to consider the local backup as well. For example, breaker failure protection would be considered as local backup, and you can run these studies to measure and check those time intervals also, if you need to do that. So I hope that was helpful. Yeah.
Also, I have some questions about the CAPE software. So my first question is, can it, because I think you mentioned something about closed loop testing. So like, can it handle like hardware in the loop testing? That's one. Two, I know the different protection relay manufacturers, they have a lot of things in common, but they also have some different things in the relay itself. So how, like a typical relay in the CAPE, what's the architecture you use to build the relay? Like, is it the Siemens architecture, or is it like a general architecture? Because, for example, now, like if you look into different relays, you probably see different names for maybe like the tripping curve. Like you might see like the IEEE tripping curve, the IEC tripping curve in one, and in another relay, you would see something totally different, not even named. So like, how is the typical relay designed in the CAPE? Is it based on what we have in the Siemens relay?
Okay. Yeah, great, really great questions. So first, let me address your closed loop comment. That the closed loop I meant was in the context of the connection between CAPE and PSSE. So there, every time step in the simulation, PSSE and CAPE are talking to each other. So I meant closed loop in that that scenario. So we don't really communicate or do a hardware in the loop kind of testing with CAPE. That's not what it's for. However, we can create test files. For example, if you want to test your relay with a Doble or an Omicron relay test set, we can create those files out of CAPE, and then you can just play it back on the test set. So that is possible, but it's not a conventional, like not a regular hardware in the loop kind of testing. The second point, how do we model relays, right? So we model the relays based on the actual manufacturer data that we have available from the relay vendor. So I'm just showing you here the CAPE relay library. It's a full list of all the relays we have in our system. And you can see, there are many different kinds of manufacturers. So if we look at Siemens, then these are all the various relay types that we support. So any one relay you pick, for example, a 7SD52, right? It's a Citrotech 4 kind of relay, and just look at the settings that are available. So these are the setting names for in the relay, and they are specific to Siemens. And then as a user, you would basically enter data for these setting names. But if you look at a SEL relay, Schweitzer relay, SEL, say 4411L, right? That's a line differential relay. The setting names for that are completely different because Schweitzer has its own way of modeling the relays. So our philosophy is to develop the relay model, the functionality specific to relay vendors themselves. So we take a lot of effort in creating these models so that they accurately represent the actual relay behavior. And now, right, a lot of the relay information is also proprietary, right? The relay vendors will not divulge or expose internal algorithms like how do they do signal processing, what kind of filtering they do. So those things, again, CAPE doesn't need, because we are again in the steady state domain. We're not in the transient, electromagnetic transient domain. So we're not really worried about how the phasors and filtering and all that is done. But once the voltage and current phasors are calculated, how are the protection algorithms applied, that we can get, most of that information is available in the relay vendors' manuals. So we take a lot of effort in actually programming those equations, considering the various supervision, internal logic, all that, whatever we can get from the relay manuals, we try to incorporate into the relay models in CAPE. So it's very detailed. It takes a lot of effort to build and get a relay model to work.
Okay, thank you. Yeah, lastly, which is the most important question. So can we get the software like a student version software for free?
Yeah, there is a demo student version available. And if there is say you have a lab in which you have some exercises and classes which need CAPE, yeah, we can do that. And there are other ways we can provide demo versions through the university, I suppose. That so yeah, there are ways to get the free version of the software.
That would be nice. Thank you.
Okay.
Any other question? Anyone? One question, when you define those contingency in your simulation, so how do you model the topology change over there? So for example, if you have 100 buses, what is the common practice in industry? So is it, if you want to do for given line, is it just you consider the topology change only around that line or not? You consider all of it?
Yeah, that's a good question too, right? So what we do is once you have identified where you're doing the study, right? So we want to study this line. The most common utility practice will be to remove, right? When you're studying this line, you may just outage. Let me go here. So the system normal you do, then you may outage this line and run the study, right? So that line is out of service. You repeat the study, then you change your outage to this line, and then you repeat the study. So the most common way to do it is to look at the line terminals, this side and that side, and then determine, immediately connected lines are removed from service. That's what most companies will do. You have to consider mutually coupled lines. If they're coupled in the zero sequence, then it has an impact on the ground fault relaying. So you have to consider those. Those are what we call the N-1 type of contingencies, where you remove one object, usually at the line terminals, one at a time. Other than that, you can also define your own contingencies, where if you have some critical generation in the system or nearby that you want to outage, then you can consider that as added contingencies. And again, all of this can be stored in configuration files and recalled, every time you repeat. But common practice is to look at the immediate line terminals and outage the sources of fault current that are immediately connected there.
Oh, that's good. That's good.
And sometimes utilities will do it, normally N-1 is the standard, because once you go beyond N-1, it becomes harder to coordinate and achieve selectivity. So they may do the study, but they may not really mitigate the issues found, because it's just too much you have to spend a lot of money to mitigate. And then you have to make a decision, do I need to or not? That's there as well.
Thank you. Thank you. Any last questions? If the lucky person, there's no lucky person.
I just have one quick comment to say.
Oh, sure.
I think probably the question you were asking is maybe related to more of a subsystem identification. That was the topic of a PhD dissertation of Dr. Ramaswamy, who also was at CAPE in the 80s. So his thesis was given an event, how do you identify a subsystem so that you can study within the subsystem and not the entire system?
Right. Yeah. So that's another important comment, right? So when we're simulating faults, let's say on this 230 kV line, do I need to evaluate relays from everywhere in the system, right? And you don't need to. Like once I go maybe 2 or 3 buses away from where I'm located, the relays are not going to be sensitive to the fault condition. So it's a parameter that the user has to set, and we typically set that to around 2 buses, sometimes 3 buses, real buses away, and capture all the protection and simulate that. But yeah, that's another point to consider as well. But the outages themselves are usually around the line of interest, right? And if you're studying this line, then local and at each terminal you consider outages, and there is a scope to enhance that as well and go beyond the immediately connected sources.
Okay, thank you. We really appreciate Ashok. That was really a very informative talk. We really appreciate for the time you spent to discuss this issue with us. Okay, with that, thank you, and hopefully see you sometime soon.
Okay, thanks very much. I enjoyed myself. Yeah, good discussion.
Yeah, okay. Thank you.
See you. Bye.
See you. Bye. Bye.